In supervised learning, the objective is to process a dataset of feature vectors and learn a mapping function that reliably assigns them to precise output labels. Powerful models like deep neural networks operate as opaque boxes. They yield highly accurate predictions, but their internal logic remains hidden from the user. The decision tree is a white box model. Its internal logic is visible and interpretable, allowing the user to follow every step of the decision-making process. It functions as a hierarchical flowchart, translating high-dimensional data into a sequence of Boolean logic. It breaks complex predictions down into discrete if-then-else rules. In environments like finance or medicine, this transparency is a requirement. Algorithmic accountability is often as important as predictive accuracy. To examine the architecture, consider a standard classification task, predicting whether a person will default on a loan based on income and credit score. The model starts at the root node. This is the topmost internal node of the tree, representing the most mathematically informative data split in the entire dataset. Moving down the branches, we encounter internal nodes. These feature tests further subdivide the data based on specific criteria. The structure terminates at leaf nodes. These endpoints contain the final class prediction derived from the sorted data. A human can read this tree immediately, but how does the machine determine which variable to test and where to set the threshold at every specific node? The tree is not built through intuition. The structure is generated through a deterministic sorting algorithm. Decision trees are constructed using an algorithm known as top-down greedy induction, or recursive partitioning. The process is greedy because it chooses the best immediate split at the current node, without calculating how that choice might affect future branches further down the tree. This chart plots the loan dataset: income on the horizontal, credit score on the vertical. Recursive partitioning divides these points into homogeneous subregions. It seeks a pure node, where 100% of records belong to a single class, isolating only defaulted users. To achieve this, the machine requires a quantitative scoring system. It must compare the purity of thousands of potential split lines across every available feature. Recursive partitioning cannot function without a mathematical metric to evaluate the quality of its own boundaries. To solve this, the algorithm relies on information theory to quantify the randomness in a dataset. This is the formula for entropy. It calculates the sum of the class probabilities multiplied by their base 2 logarithms. The curve shows that entropy peaks at maximum unpredictability. It drops to precisely 0 when the data is perfectly pure. For example, if a node contains exactly 50 low-risk cases and 50 high-risk cases, what is the calculated entropy? The math evaluates to an entropy of exactly 1. Because the classes are equally distributed, the node is in a state of maximum impurity. Many algorithms use an alternative metric called Gini impurity. It is calculated by subtracting the sum of the squared class probabilities from 1. Gini is computationally faster because it avoids logarithmic operations. In practice, both metrics yield similar ratios and generate nearly identical tree structures. These impurity metrics provide the objective criteria for every structural division the algorithm executes. This calculation represents information gain. The algorithm calculates the impurity of the parent node and subtracts the combined weighted impurity of the resulting child nodes. The machine tests every possible threshold for every feature. The attribute that yields the highest information gain is selected for the split. This works for categorical labels. But what if the target output is a continuous number, like a loan amount in dollars? For continuous targets, the architecture adapts into a regression tree. The structure remains the same, but the splitting engine uses a different mathematical approach. Regression trees abandon entropy and Gini. Instead, they calculate splits to minimize the mean squared error of the numerical targets within each partition. When a new instance reaches a leaf node, the tree predicts its value by calculating the arithmetic mean of all the training examples stored in that leaf. The same recursive geometry transitions from discrete classification to continuous forecasting. Consider what happens if we allow the algorithm to partition data indefinitely, stopping only when every leaf node has an entropy of 0. The model will achieve a 100% accuracy rate on the training data. A perfect training score indicates the model has failed its primary objective, the ability to generalize to new data. This is overfitting. By isolating every individual instance, the model memorizes the noise and anomalies of the training set instead of the underlying statistical patterns. To create a functional model, we use pruning to stop the tree from memorizing the data. We can apply pre-pruning during construction by setting hyperparameters. For example, we can set a maximum depth for the tree, or require a minimum number of samples to allow a split. We can also use post-pruning. This involves growing the full tree first, and then trimming back branches that do not improve performance when tested against a separate validation set. The value of a model is measured by its performance on unseen data, not its ability to memorize the past. The primary strengths of the decision tree are its white box interpretability and its computational speed. Unlike distance-based models, the tree evaluates features independently. This means it requires no feature scaling or statistical standardization before training. The trade-off is high variance. Because the model is highly sensitive to the training data, minute shifts in the input can lead to a completely different tree structure. The algorithm also has a structural bias, as it naturally favors features that have a high number of distinct categorical levels. While a single decision tree is a capable baseline tool, this sensitivity to data often prevents it from being a standalone enterprise solution. This leads to a new question. If one tree is sensitive to noise, what happens if we build 100 varied trees and calculate the outputs of their outputs? This is the logic behind ensemble methods and random forests. By aggregating multiple models, we neutralize the variance found in individual trees. You can test these parameters yourself. Initialize a decision tree classifier in scikit-learn using the standard iris dataset. Toggle the criterion between Gini and entropy and experiment with the max depth setting to see how the leaf structure responds. Understanding the architecture of these models requires testing the theory through active programming.